We're just going to consider bars along here. The number of bars in this particular pattern does not matter. Right? Now, again, what we've got here is that gamma h is the distance between bars. So from the neutral axis, it's half gamma h. Now, this gamma value, we don't need to calculate. We do actually have this table here, table 7.2, which allows us to figure out for a particular size column and a particular bar size what that value for gamma is. Right? So this takes account the cover distance and the stirrups and automatically figures out what gamma is. So this first one here is 40 millimeter cover, which is 10 end ties, and then we also have 50 millimeter covers to 10 end ties, table down here as well. So it's just a matter of looking up on the table what that value for gamma is for your particular configuration. All right, so again, we start by coming up with our PF and setting that equal to PR and going back to this table and reading across and coming up with our first guess of our size. Right, that first guess of that size, we can then go back down to this table and figure out what gamma is. We're going to guess what size reinforcing we're going to use. And so I just pull gamma off of the table, and then we're going to do all of our calculations based off of that. So again, what we're going to do here is figure out the moment of inertia of the steel. And this is just going to be plus 80 squared.
So on that one was H is 400?
Yeah, so the tables are all done in terms of the generic value for H. Right, so our I of our steel is plus 80 squared. So it's our area of our steel times gamma squared, H squared over 4. Right, so that's our area times distance squared. Now, again, we don't necessarily know what size bars or how many bars I'm putting in there when I look at this formula. So what I'm going to do is I'm going to relate this back to that reinforcing ratio. So that's that rho value. So rho T is area of steel divided by BH. Right, we looked at BD when we were talking about beams, but here we're looking at gross area for our columns. But again, it's just a reinforcing ratio. So if I plug that reinforcing ratio back in here, what we end up getting is rho T gamma squared BH cubed over 4. And if I take this expression, I take this expression and substitute that back into our PI formula, I got my 0.2 ECIG plus ES rho T gamma squared BH cubed over 4, and all divided by 1 plus beta D. Now, this formula, yes?
Where does the 4 come from?
Because it's 1/2 squared.
Okay.
So what this formula is fairly complex. But you'll notice that I've got a BH cubed term out here, and IG, of course, is 1/12 BH cubed. So what we're going to do is we're going to rearrange that equation a little bit, and I'm going to factor out a little part of it. So our EI is EC over 60 plus ES rho T gamma squared over 4, and this will be times BH cubed over 1 plus beta D. And what we're going to do is take everything inside the square brackets and let it equal K. So this is equal to K times BH cubed over 1 plus beta D. So all of this inside the square bracket. Now, let's go and take a look at bars on the side faces. Right? So that last calculation was bars on the end faces. And with bars on the end faces, it really didn't matter how many bars that I were looking at, whether it was 5 per side or 6 per side or 2 per side. It really doesn't matter because it was just plus 80 squared. And we considered this area of steel term would be worked into our row, right? So the number of bars weren't really critical. We did the calculation exactly the same. When we're looking at bars on our side faces now, when I plug in our plus 80 squared, again, we're going to neglect the moment of inertia for each individual bar. These bars out here, I'm going to do exactly the same calculation as we did before. So 2/3 of the bars are going to be effective at coming up with that moment of inertia. But these two bars right here lie right on the neutral axis. So when I plug in a plus AD squared, the distance term for those is 0. So in other words, this is not as effective as putting in just 2 bars on each side without the additional bars along the side faces. Right? So what may seem kind of counterintuitive is that the eye of the steel goes down the more bars you put in when they're on the side faces, because more of that steel is closer to the middle where it's less effective. Right? In this case here, what we would end up putting for our eye steel is 2/3 is our AST gamma squared H squared over 4, and plus 1/3 times 0. Right? This part here is exactly the same as what we did there. Right? 2/3 of it is effective, but 1/3 isn't. So when we calculate this out, what I end up with is a rho squared gamma squared BH cubed over 6. Right? So instead of over 4, it's now over 6. And what you'll see is that for different patterns of reinforcing, the number that changes is this one right here. Right? And that only affects our K value. Right? So the rest here, we end up in the BH cubed over 1 plus beta D. That's all exactly the same. Right? K changes. Right? So this was 3 bars. 3 bars. If I do the same thing with 5 bars, right, so we look at a configuration like this. All right, I get our eye of steel is 2/5 times our AST gamma squared H squared over 4 plus 2/5. It'll be AST gamma squared H squared over 16. Right, so these 2 bars right here have a different distance term. Right, that's where the 16 comes from. And this will calculate out to rho squared gamma squared BH cubed over 8. And so more bars, bigger denominator, IST is going down. For 7 bars, it's over 9. Your theoretical limit. So a theoretical limit assumes we have a solid block of steel in there. The denominator becomes 12 for that theoretical limit. If you go with a practical limit of 6 bars, that number works out to 8.57. And the last one that we'll look at is equal reinforcing on all 4 sides, which is a combination of these last 2. Right, so remember, the first one we looked at was bars on the end faces. That was divided by 4. And we looked at bars on the side faces, and here, different pattern. Right? The more bars we get, the less effective the steel is in terms of resisting the bending. So let's go with all four sides. And we'll go with 6 bars per side. And the denominator becomes 5.88 in that configuration. Now, it's not really all that necessary to go through and do extensive set of calculations for this, because what we're looking at is a set of interaction curves where we're going to be pulling off the behavior of our column. Right? Now, these interaction curves, this used to be the single largest section of the concrete design handbook. Right? There's pages and pages and pages of interaction curves. Right? So there's so many of them that now they've decided that they're going to put them as a separate download. Right? So this is that Chapter 7 additional design aids. Right? And these are what your interaction curves look like. And there are pages and pages and pages of them. So for different configurations. Right, so just let's go and look at the first one here for a minute. Right, so what this interaction curve does, and the way it works is fairly straightforward, is we're going to have a curve that matches our particular column. Right, this particular one is based off of an F prime C of 25 MPa and a gamma value of 0.6. Right, so what we're going to do is first of all identify for our particular column size that we're looking at what is F prime C and what is gamma. Right, so we're going to have like 35 MPa and a gamma of 0.7. Right, so I'm going to find here 35 MPa, there's a gamma of 0.7. Right, so it's just a matter of hunting down to find the right page. Yes?
Where can I find these in this book?
They're not in the book. They're separate download. Right, so if you go to the website where you had the link to find the book, there'll be a separate download link for the PDF right there.
Will we need those?
Yes. Yeah, so when you're looking at doing these calculations, these become critical. So what we have is the vertical axis is our axial resistance, and our horizontal axis is our moment resistance. Right. So again, they're set for PR and MR. So basically, what we're going to do is set that equal to PF, and we're going to set that equal to MF. Now, our MF is either going to be M2 or MC, depending upon whether we've got a slender or non-slender column. Right. So it's just a matter of calculating this value. PF over AG. Right, so again, we've got an AG value for our column size that was listed. So it's just a matter of pulling off a value and coming up with a value in here and drawing off a horizontal line. Right, and then I'm going to do the same thing with my MF over AGH. And I'm going to come up with a value and I'm going to draw a line. And where those two lines intersect, I've got a point. And that point is either inside of this curve or it's outside the curve. If it's inside, it works. If it's outside, it doesn't. And it's basically, it's as simple as that. Now, what we have here are a variety of different curves based on different reinforcing ratios. So 1%, 2%, 3%, 4%, and so on. So for whatever reinforcing pattern that I've got, if I go back and I'm looking at some particular configuration, right, and we're going back to these ones right here, and I look at, say, a 400 by 400 column. That's 2 faces. Let's go with 4 faces here. There's 4 faces. Let's go with the 400 by 400 column. So I'm looking in this configuration right here. And I say, okay, let's choose a pattern where I've got 2.5% reinforcing. So now I'm going to go to my table. And I say, okay, I need something halfway between the 2% and the 3%. So I'm going to interpolate the curve halfway in the middle here. So I have that new interpolated curve. That's the one for our column. So now I'm going to calculate this quantity. I'm going to calculate this quantity. I'm going to see if that point is inside or outside that interpolated curve. Inside it works, outside it doesn't. Now you'll notice in here that in addition to reinforcing ratios in here, there's a K value listed. This K value is this one right here. So if we are doing a slender and we have to take into account our buckling or the P delta effects, and we need the EI for the P delta, here I'm going to calculate the EI based off of that K. Right, so I'm just going to go and pull off the K value right here. So again, if I'm interpolating a curve at 2.5%, I will interpolate K in between those two values. Right, so once I get that K value, I just stick it in the formula. I've got my EI. That goes into my PC formula, and then continue on. Yes?
Our gamma is
That's a good question. What you'll see here, let's move the head out of the way here. What I'm going to do, let's look at our 2% curve here. So there's our 2% curve. Not bad. And I'm going to go, this is a gamma of 0.7. So what I'm going to do is go up to a gamma of 0.75. And let's see if we can line these up properly. So it's going to be 10, 15. And this here is 2, 3. See how they line up. So I'm going to go up to a gamma here of 0.8. And you can see that they don't quite line up perfectly, but you get it's not going to let me line it up exactly, but okay. So what we're seeing here is that this was our 2% curve, right? And this part here, right, the difference here between our 15 and 15 is about the same as what we have here. So this part of the curve is lining up exactly the same. Right? There's no real movement out here. But what we're seeing with our 2% curve, right, so this is our 2% curve coming down here, is that the nose of this, right, again, here this is our 3, right, so if I take this section right here and move this out, what happens is this nose of this curve is actually moved out a little bit. Right, so what you're seeing is that, I'm going to look at here kind of where the nose of that 2% is. Right, so the nose of the 2% was coming out here at a value of about 3.8. And as I go up here to 0.8, 2% curve, the nose goes up to 4.2. Right, so here it was 3.8, and here it is 4.2. So the higher value of gamma, what that means is the higher the value of gamma, the more this curve is being pushed out that way, right? Which means that what we get is a higher moment resistance. So that means it is conservative to round down your gamma. If you round down your gamma, that means the nose of that curve is pulled back, and so you are not getting as much moment resistance as you would have. So it is conservative to round down. Okay, let's go and take a look at some examples here. We'll go with a 350 by 350 column. 3-meter high. Got prime speed of 35 MPa. And FY of 400 MPa. Our PF is 2,500 kilonewtons. M1 and M2 are going to be 40 kilonewton meters and 80 kilonewton meters. Say this is in double curvature. And we're going to use 40 millimeter cover to 10 M ties.